on, okay, because obviously the government cares about it. So I established the Galileo project to do that, and we now have a suite of instruments that takes a video of the sky in the infrared, in the radio, in the optical, and in audio, and we will use artificial intelligence to digest the data and tell us whether we are looking at a natural object like a bird or an insect, or whether we are looking at a human-made object like a weather balloon, a drone, an airplane, or a satellite, or something else. And, we should behave like kids. We shouldn't assume that we know the answer, like the experts always tell you. Because one of the biggest traumatic experience I had as a kid was coming to the dinner table, asking a difficult question, and then seeing the adults in the room dismissing the question because they didn't know the answer. And I thought that by becoming a scientist, I would figure out the answer myself. I don't need to pretend that I know more. We can just be guided by evidence. That's the way science is done. But unfortunately, it's really strange, but even within science, the practitioners want to maintain an image of an adult, the adult in the room, to pretend they know more than they actually know, and to avoid collecting evidence because that would be a reputation risk if it turns out that it violates what they said initially. Also, if it's something really new, it would imply that as experts, they did not anticipate it. So they would rather argue, Oumuamua must have been a rock of a type that we've never seen before because that's natural.
Keeps them the expert.
Keeps them as experts. Yeah. It's just that, it's a natural object from another type. There are different types of rocks, not a problem.
So as we've been going for an hour 25, so I want to move on to something everybody's interested in, which is black holes, right?
Okay.
One of the most fascinating and weird things probably in the universe. Albert Einstein, as he worked out his theory of relativity, as he kind of theoretically thought about the prediction of something like a black hole, he thought his theory must have a flaw because it was just so unbelievable. Why are black holes so unbelievable? Like, what is it that spooked Einstein to the point where he's like, this is impossible, this theory is wrong? Obviously, we've proven, and we've even observed them now, that they are real and they're out there.
Right. So the thing is that Einstein's theory of gravity predicts that it's basically says that it's incomplete, in the sense that a black hole, at the middle of the black hole, there is a singularity of space and time, meaning that if matter, just imagine a star collapsing, which actually happens for stars more massive than 8 times the mass of the sun. They usually consume their nuclear fuel and then collapse, okay? And if the star is more than 15 times the mass of the sun, then it could end up in a black hole. The core of the star simply collapses to a point. And just think about it, it goes all the way to a point, and eventually you get a very extreme curvature of space and time. Einstein's innovation was to argue that space and time are not rigid. It's just like the surface of a trampoline. If you put a heavy ball in the middle of the trampoline, then it will curve the surface. And if you have a marble that you send on that curved surface, it could move in a circle around the center, even though if you were to take out the ball from the center, it would move in a straight line. So that is the analog of a planet like the Earth moving around the sun. Gravity is not a force, it's the curvature of space and time. So the Earth wants to move straight. So if you remove the sun, the Earth will continue straight, just like the marble on a flat surface. But because of the sun, like this ball that you put in the middle, the space is curved, such space and time are curved such that the Earth moves around the sun. And that's what gravity is, according to Einstein. So, but in the extreme case, if you pull the surface of this trampoline too much, it tears apart somewhere. And that's the singularity of a black hole, okay? And that means the theory breaks down. And we know why it breaks down. It's because it's incomplete. It doesn't have quantum mechanics. So we know that once you get very close to the singularity, quantum mechanics matters, And we don't have a theory that unifies quantum mechanics and gravity. Einstein dedicated the last decade of his life trying to figure out a theory that unifies quantum mechanics and gravity. We are still trying to do that.
The theory of everything, they call it, right?
Yeah, it's not really everything. By the way, the reason it's not everything is, there is this tendency of physicists to say that we will reduce nature to some simple fundamental laws. But what they are missing is that complex systems, even if you have, let's say, the laws of chess, you would never appreciate just from the laws of chess how amazing a master is, because from the same laws of chess you can have different moves. And looking at complex systems that use the same fundamental laws of nature, understanding the laws is really a very small part of the puzzle. You want to understand complex systems, how they, like life. What is life? That will not come out of physicists understanding the theory of everything. You have to figure out what is intelligence, what is consciousness. These are questions about complex systems. By the way, I think consciousness is nothing special. It's just that the system is complex. And when we die, it's just like unplugging a computer from the wall. Basically the system shuts off, and in principle we could live forever if you just figure out how to repair this body so that it will not disappear. So eventually we might live for a very long time. I don't know if it's a blessing for everyone, but you will have a choice. So the point is that when you deal with complex systems, things are more interesting and beyond the fundamental laws, and I think in the future that will be the focus of science. It's not the fundamental laws. Like physicists were very proud that they're leading the frontiers, but that's not really the most challenging task that we have. It's to understand complex systems and replicate them, like intelligence, consciousness, all these AI systems. They will become sentient, and then we will realize what sentience means. So anyway, coming back to what so we were talking about black holes, and black holes are they have these singularities where Einstein's theory breaks down.
Why does it break down at a singularity?
Because the curvature of space and time becomes infinite. So it's like a very extreme. By the way, I had the...
It makes no sense.
Yeah,
for it to be infinite.
Well,
like,
it cannot be infinite. Something must correct it, and that's quantum mechanics. By the way,
why can't it be infinite?
Because eventually you reach curvature of the trampoline such that it will tear apart. So in the case of Einstein's theory, you reach a curvature of space and time such that quantum mechanics matters. Okay? You definitely have to include quantum mechanics at some scale, and that's what we are missing. But I should say, I had a flood in the basement of our home a few years ago, and I called the plumber that came over, and we found the tree roots in the sewer. Okay, I helped him to clean it up. And by the way, I enjoy the company of people that don't know much about science. I really love to speak with them. What?
Peasants.
Not peasants, like me. I mean, I grew up on a farm, so I completely relate. So anyway, I then thought to myself, I never thought that the water from my house goes somewhere. There is a reservoir of the town where it goes to, like through the sewer. And I never thought about it until it was clogged. So that led me to think, what happens in the middle of a black hole? Where does matter go?
It's going somewhere, right?
Somewhere.
Yeah.
And one possibility is that it's clogged, the singularity is clogged, and you build up an object with very high density, just like an extremely dense star in the middle of a black hole. That's one possibility.
It's just a big star, but it's too heavy.
It's extremely dense, but you can't see it because it's hidden behind this event horizon. You can't see through it. But if you wanted to see what's there, you can jump into a black hole. And I recommend to many of my colleagues who study string theory, if they want to test their theory, they should get into one of the nearby black holes. And they say that I have an ulterior motive to send them there.
Yeah. So, but I guess it's going somewhere, but it's not, because the mass doesn't disappear, it stays there, or it radiates away.
So there are two possibilities. Either you collect the mass in some extremely dense object, the highest density possible. It's called the Planck density, where quantum mechanics matter. You can have a Planck density object, extremely dense, sitting there and collecting everything that falls. Another possibility is that it goes somewhere else, like another universe or somewhere. We don't know.
But the mass does stay there. So is it
Yeah.
possible that it goes somewhere else, but also it holds the mass there? Because it,
No, it needs to be there.
Yeah.
By the way, Stephen Hawking, we mentioned him before, he realized that black holes eventually evaporate.
Hawking's radiation.
Hawking radiation. And by the way, he discovered it because there was a young student at Princeton named Jacob Bekenstein who suggested that black holes, based on what Hawking derived earlier, that when two black holes merge, the area always increases. That's what Hawking showed. And so Bekenstein said, well, maybe it means that they have entropy. They have some information on their surface, and according to thermodynamics, entropy always increases. And so the area of a black hole always increases because it has some entropy on it. And Hawking said that makes no sense whatsoever. Who is this student saying that? Just like in the case of Cecilia Kovarsky. And his goal was to prove him wrong. And he did a calculation, realized, oh, he was right, Bekenstein. And in fact, black holes have entropy, they have a surface temperature, and that means they radiate, and that means they evaporate. So he wrote a paper about it. That was his most important result. Just like in the case of the sun, with Henry Norris Russell. So, what I say is never dissuade a brilliant graduate student. Or if you don't believe what the student's saying, try to prove the student wrong, and you might find the most important result of your life.
How is it possible that it can radiate energy or mass away when light, which is pure energy, right, can't escape it?
Oh, it's very simple.
Yeah.
The black hole, as I mentioned, has an event horizon, right? So there is a size to the prism. So imagine a prism that has some size, okay? Obviously, if you want to put a person in the prism, the person has to be smaller than the size of the prism, right? You can't push a person into a small cavity that, is too small, okay? So now, light is made of particles. They're called photons. And the wavelength of a photon, which is basically, a photon is just an electromagnetic wave that has a certain periodicity over some distance. The wavelength represents how compact is the region that you can localize a photon. You can't put a photon in a region that is smaller than its wavelength. That's the minimum size of a photon, a particle of light. So now imagine a photon, a particle of light that has a wavelength bigger than the black hole. You can't keep it in the prism, okay? So the black hole would lose this photon. That's the Hawking radiation.
I see it.
So it keeps losing particles because they're bigger. They have a wavelength comparable or bigger than the size
And
of
it's very, very slow, right?
It's very slow because these for astrophysical black holes, they are quite big. So these wavelengths are very long, and that means the particles carry very little energy, and therefore the evaporation is very slow. But if you made the black hole very small, then it would explode quickly.
Oh, it would explode.
Yeah.
Is it possible, it seems like the black hole is such a attractive place for imagination. What goes on in the center? You think about the Big Bang. Is the Big Bang a singularity or a black hole?
So that's another singularity, I should
You
say.
know.
So Einstein theory breaks down in two places. Black holes, that's one singularity, when
Right.
a star collapses to a singularity. Another is the Big Bang. We know that the density was infinite of matter there.
So it's like the center of a black hole.
Yeah. So then the question is, what was before the Big Bang? And we don't know the answer because we don't have a theory that unifies quantum mechanics and gravity.
It is possible that we are all in the center of a black hole.
Well, the singularity of a black hole is different. There are similarities.
How do you know it's different? I'm just curious.
Because when you make a black hole, there is a finite region of space that from where you gather the matter that ends up in the singularity. Whereas In the Big Bang case, it's actually an expanding situation, that you start from the singularity and you're expanding out. And it's a singularity in time, not in space, because there was a point in time when the density was infinite, and then...
Actually, I want to ask you about a theory I just recalled. So we're talking about heat death and about the origin of the universe. Is it possible that, like, in unfathomable, trillions, hundreds of trillions of years, so there's a total heat death in the universe. There's like nothing left, basically. So one thing I heard that was really interesting is that in the ultimate heat death, the fact that basically there's nothing left turns it almost back into a weird way, a singularity again, where because like the space basically disappears, it becomes homogeneous. It's like one uniform space.
Yeah.
Is it possible that in a weird way that is able to once again become a singularity as space becomes irrelevant almost?
No, I mean, it's not. I mean, think of it as a death of a person. So it is a simple state, but it's not the same as the initial state. And as I said before, we don't really know the future, in the distant future, because perhaps we are wrong about how the vacuum will behave. We don't know what the dark energy is, and maybe it will decay or something will happen to it, and the universe will stop speeding up its expansion. And maybe after that it will contract. So there are suggestions that maybe the universe is cyclic. It's just going through cycles. We have to live that long to figure out what happens. For now, I mean, I should say there is another passion in the study of the universe, and that's called the multiverse. We think that, in fact, there is much more outside the region that we can see. So there are other regions like our universe, but they have conditions very different than we have. And in fact, anything that can happen will happen in infinite number of times. So if a kid gets a bad grade in an exam, let's say he gets a C, the kid shouldn't feel bad about it, because there are many other regions of space and time where the kid gets a good grade. But I think of this as just like living in the metaverse. You can never test it. Therefore, it's not really science. It's sort of like a mental drug. I mean, so humans are attracted to imagined realities. They're attracted to those realities that flatter them. I'm not. I want to know. I want to see the pimples on the face of reality. I don't want it to look beautiful, because I want to figure it out. That's what I want. And even if it doesn't flatter me, I want to know what it is. To me, that's the meaning of true love. If you are in love with a person, the meaning of love is not to idealize the person as perfect. The meaning of real love is to notice the faults of the person and to nevertheless love that particular unique thing. And you can feel the same way about reality. You don't want to idealize reality, to make it the way that would flatter you the most, that you would imagine it like science fiction would imagine it. You want to know what it is, and then you will have a better connection to it. So, and another thing is, a lot of scientists in theoretical physics, they prefer to do mathematical gymnastics to demonstrate that they are smart. And I say, doing physics is not about showing that you are smart. Because, for example, if we discover aliens, extraterrestrials, you may not need mathematical sophistication to understand that. Nevertheless, it would be the most fundamental realization that humanity ever made if there is another civilization. So showing off by